Good morning. I'm Soham Chaudhuri, and I will be presenting the paper KGAN-Based Semi-Supervised Domain-Adapted Human Activity Recognition. Um, Human activity recognition has been one of the most explored areas since the introduction of AI in sensing. Sensors have been part of handheld electronic devices for a long period of time, and the inclusivity of AI has boosted the functionality of sensors even further. The aim of this study was to develop a model that can generalize across multiple domains for predicting the activity that is being sensed by sensors. So many studies have been done in this specific domain of study. One of them being from Yang et al., who implemented a transfer learning solution, and another one being by X Fang et al., who have introduced a multimodal solution to the problem statement. The problem right off the bat that we face for this problem statement is the limited labeled data that is available. So the introduction of GANs was extremely popular to handle this situation. The synthesizing of synthetic data that allows us to generate pseudo labels to mitigate the problem of unlabeled data. The dynamic relationship between the generator and discriminator help us generate the source data that helps to increase the amount of data that can be used for training. To help us with the domain adaptation problem, the source and the target domain relations, we use a KMM method, the kernel mean matching, that we will talk about in the next few slides. The GAN model that we have implemented uses the Kolmogorov-Arnold representation theorem, which has a property of universal function approximation. This specific method allows us to have dynamic activation functions and makes it more robust for domain adaptation purposes. To guide the generation of synthetic labels, we use MMCD, the maximum mean covariance discrepancy, as a metric, a loss metric that helps us in the training of the weights during backpropagation. Most unsupervised models that are used today do use a pseudo-label method of generating more training data. The overall architecture uses the kernel mean matching, the GAN, the K representation theorem, which is integrated within the GAN framework, and the maximum mean covariance discrepancy theorem, overall to help us generalize to the target domain in a more efficient manner. And leveraging the K representation theorem, we are able to have a more structured way of approaching the domain adaptation process. The GAN models that we have used work specifically using the K representation theorem instead of the normally used person-prone models. The data that we have used is from accelerometers and gyroscopes of various hertz. The complex multivariate functions that are developed because of the time series based data we are able to deconstruct it to univariate functions with the help of this representation theorem, which helps in the classifying of the overall model. In this study, we have induced a manual domain shift to test the model. The domain shift is done by scaling and rotations, similar to that of the affine transform. The manual domain shifting is done due to observing the robustness and to keep an eye on the covariances that may go unnoticed during training. The framework of the overall model is represented in the diagram. That it is basically the data flow through the entire work process, and also the loss metrics that we can see in the backpropagation and optimized part of the workflow. The kernel mean matching method works on the principle of the RKHS, or the reproducing kernel Hilbert space. The basic use of the KMM is to reweigh the source samples in a way that they represent the target domain in a simple fashion, so that we are able to maintain and retain the data of the distribution in general, and as well as have a easier way of representing complex relationships between source and target domain. The K representation theorem in the GAN framework is represented by the following formula of GZ, where X being the output. We can see the integration of univariate functions, where the univariate function is the psi ij with an input of Zj. The overall formula helps us represent complex data distributions and also allows for a more simple method of representing a dynamic activation function. The following slide shows the basic formulations that of the generator and the GAN interaction. Other than that, we also see the loss formulations in the future slides. Go forward with that. The loss formulations first would be of the KGAN model. The KGAN model regularization losses are represented by the following formula, where lambda1 and lambda2 are regularization coefficients, while pi is the normalization factor. The loss function that is calculated is the L total, which is the sum of the L weighted and L KGAN regularization loss, where L weighted is the sum of the L MMCD, so the loss calculated by the maximum mean covariance discrepancy, and the loss calculated by the KMM's weighted approach. So addition of that along with MMCD, of course, there are importance factors as well. So the importance factors will weigh at what degree the metric will have an impact on the training. The computational complexity of the model turns out to be O of n squared d, which is standard. The only point to be observed is that the KMM does have a complexity of O of n cube, but since it's a single time computation, the overall complexity is O of n squared d. The data that is used are the UCI HAR data and the HHAR dataset. The UCI HAR dataset consists of the accelerometer data and the gyroscope data, while the HHAR dataset also has accelerometer data, which consists of more number of sensors specifically. The ROC curves of the training purposes are shown, which represent the true positive rate versus the false positive rate of the training. The overall results, we can see the comparison that the proposed model for HHAR predicting an unlabeled target domain dataset is around 20% more accurate, while the UCI-HR, it has around 2% higher accuracy. This is represented clearly here. The macro averages and micro average F1 scores are also shown in this specific slide. The use of KMM and MMCD have balanced each other, which helps guide the domain adaptation processes more easily, where KMM can help maintain, show us the distribution differences, and MMCD being a metric that shows the distances between the domains and within the domains, source and target domains. We can show a direction for the generation of the data to bridge the gap between the source and the target domains, hence making it possible for us to train a completely unlabeled target domain. In conclusion, the HAR data being highly multivariable, we can have improved classification accuracy using the Kolmogorov-Arnold representation theorem. The robustness of the model is tested well in a semi-supervised environment, and the scarcity is handled using the Kolmogorov-Arnold representation method. The superiority of the performance has been observed in the previous table. Future work is being done to make the model more robust and to handle the standard deviation problems that the model sometimes shows. Thank you.